Okay, so today we're going to start with a quick review of MOSFETs. We talked about using MOSFETs for motor drivers last time. We talked about how we could use them to just turn the motors on and off, and we also use them to control the speed of motors. So we'll do a quick review of that. We'll talk about using pairs of MOSFETs to create CMOS devices. And then we'll talk about H-bridges. So we were able to control the speed of the motors last time, but we were not able to control the direction, right? We could turn them on, we could turn them off, we could control the speed, but they were always going the same way. H-bridges are circuit configurations that allow us to control both the speed and the direction of a motor. So we'll talk about that. We'll discuss how we put them together, how they work, and then we'll do a quick preview of the lab. So today you're going to build an H-bridge. First of all, you're going to build a version that controls direction. So it's just on and off. It doesn't do any speed yet, but it can control the direction. So you can make it go clockwise or counterclockwise. And once you got that working, you'll add the speed control afterwards. Any questions before we get going? Cool. Okay. So let's do a quick review of using MOSFETs as motor drivers. So last time we talked about MOSFETs, and we said that the basic idea was we had a power supply up there, and then we had our MOSFET here. And our motor was down here. Ground. So this is the gate, the drain, and the source for the MOSFET. And we said that if we controlled the voltage at the gate, that would turn the MOSFET on and off, pretty much like a switch. So that would allow us to turn the motor on and off. And that was pretty good because we could use a very small device here, like a microcontroller, to set the voltage at the gate and control a very large device over here, like a large motor or even a large pneumatic actuator or hydraulic device that was controlled by a large voltage or current. So we could take a small voltage here and control a large device. So this was pretty cool, but it had some limitations, right? If we just turned this on or turned it off, that didn't really allow us to have very fine control over the motor. We wanted to go a little bit farther and be able to control the speed of the motor. So what strategy did we use to control the speed of the motor?
Pulse width.
Yeah. Pulse width modulation, right? PWM. So we said that what PWM was this strategy for changing the voltage between the gate and the source. And we were creating a series of pulses in that voltage, right? And what we did is we said we could vary the size of those pulses or the duration of those pulses. So those pulses could be on most of the time and off for just a little while. And then that would give us an average voltage that was pretty high. We said that the percentage of the time that the pulses were on was the duty cycle. So if it was on for 90% of the time, we would say that was a 90% duty cycle. Conversely, we could have it off for most of the time, right? And on for only a short period. So then that might be a 5 or 10% duty cycle. And by varying the duty cycle, we could vary the average voltage and thus vary the speed of the motor. A higher duty cycle meant that the motor was getting more average voltage, so it would go faster. A lower duty cycle meant less average voltage, so it would go slower. I'm sorry. These pulses are supposed to be all the same height. That was just my clumsy drawing. But they're all the same height. It's only the width of the pulses that changes. Okay. And why did we want to go with the PWM rather than just changing the voltage at the gate in an analog way? I mean, we could have just set the voltage sort of halfway on and made the transistor halfway on, right? Why did we go with PWM? Yeah?
Motors don't like low voltage?
Well, no, the motor would be okay with it. But yeah, the efficiency, right? The transistor is very efficient when it's completely on or completely off, right? It uses very little power when it's completely on or completely off. When it's sort of halfway in between, it has a sort of middle-of-the-road resistance, which means that it has voltage across it and current flowing through it. And you guys remember from Watt's law that voltage times current is power. So if you've got voltage and current on this MOSFET, then it starts to use up power. It turns that power into heat. And so that's wasteful because it's energy that's not doing what you want. It's not moving the motor, and it's also it's hard to deal with that heat, right? You have to dissipate it in some way. If you have lots of these things together, then your device might heat up, and it might become dangerous to people. It might start melting solder. So it's just inefficient. So the MOSFETs are really most efficient when they're either fully on or fully off. And the PWM allows us to be in one of those two states for most of the time. It's either on or off. The only time that it's not in one of those two states is during this transition time. And that transition is very brief. It's almost vertical. So PWM is used because it's most efficient. We also talked about these resistors that were at the gate. So sometimes we would have a control that was done like this. We'd have a resistor down there, and we could have a switch up here. Yeah, it's called a pull-down resistor, exactly. And what is the purpose of that resistor? Yeah, exactly. So when the switch is closed, this gate is at a high voltage because there's a wire straight from the positive voltage to that pin. When the gate is open, this resistor allows any excess charge that was left on the gate to drain out and go down to ground. So it pulls that charge down. So that's why it's called a pull-down resistor. And it forces this gate to be at zero voltage when nothing is connected to it. If we didn't have that resistor there, then the gate voltage would be floating. That is, it would not be in a fixed or known state, and it could be affected by small changes in the environment, like somebody brushing up against it or static electricity in the air. So we want to have a pull-down resistor in order to set that gate voltage to a known value at all times. Okay. Questions about that? Yeah.
Is a resistor like a high value or a low value?
High value generally. It's usually around 10 kilo ohms, give or take. it doesn't have to be very small because the amount of charge left on there is very little. So even a high resistance is enough to drain off what little charge is there. It just has to allow that charge to go down. If this were a small resistor, then it would also be drawing more current when this switch was closed. So by making it a high value, it draws only a small amount when the switch is closed. If we had 15 volts up there, it would only be drawing 1.5 milliamps when the switch was closed.
Did you say you want it to be a high resistance?
Yeah, you want it to be a high, like 10K or maybe even higher than that. Something like that.
For Apple, we have a different voltage that prefers the transistor gate over the ground going through that resistor.
I'm sorry, say that
You
again?
want the high resistance so that basically the voltage is predisposed to go through that gate instead of down through that resistor to the ground when it's closed.
Well, right. So since this is a MOSFET, there's hardly any current that flows into the gate.
Voltage.
Right. The voltage is set to pretty much whatever your supply voltage is. So the only difference would be you could assume that this wire actually had some resistance. Then the wire in combination with this this resistor here would be acting like a voltage divider. But if you did that, the wire resistance would only probably be on the order of 1 ohm. So almost all of the voltage would be at the gate. Yeah. So, other questions about that? Okay, cool. So that was how we controlled motors with MOSFETs. Like I said when I was doing the overview, this allowed us to control the speed of the motor, but not the direction. Okay? And so today, when we talk about H-bridges, we'll find out how to control the direction as well. The other thing that we talked about last time was CMOS devices. Anybody remember what CMOS stands for?
Complementary metal oxide.
Right, exactly. Complementary metal oxide semiconductors. So, complementary usually means that there are two things working together. And that's the case here. You have two transistors that are working together. So the basic form of a CMOS device is like this. You've got two transistors here. And then you've got a couple of resistors. So what happens here is that you've got your supply voltage up here, ground, your input and your output. When the input is high, that turns on this this top transistor. Basically, this top transistor acts like a wire, and the bottom one gets turned off. It acts like an open circuit. So you have a wire going from positive voltage to your output. So that means that your output is pulled high. When the input voltage is low, then it turns on the bottom transistor, which connects the output to ground, basically. Top one gets turned off. It acts like an open circuit, so the output gets pulled low. So this allows you to set the output voltage to either high or low. When we just looked at a single transistor by itself, what we saw was that we could set the voltage in one direction. For instance, in the last case, we could set the voltage to be high, but then when the input was in the opposite state, the output voltage was just left floating. It was not pulled low. The CMOS configuration allows us to set the voltage both high and low. Okay? And we said that some applications for CMOSs. Anybody remember some of the applications for those? Yeah, camera sensors, definitely. Computer memory, computer chips as well. So these are all things, places where CMOS devices are used. Any questions about that? Last time in the lab, you guys built a CMOS device and you hooked it up to 2 LEDs. So you should have been able to turn on either one of the LEDs by setting the output voltage high or low. So that was just one large-scale example. Okay, so that's a quick review of MOSFETs used as motor drivers and also CMOS pairs. So let's talk about H-bridges. So what are they? Like I said before, H-bridges are circuits that allow us to control both the speed and the direction of a motor or another electrically controlled device. Okay? So that's the purpose. Before we were only able to control the speed, but now we want to control both the speed and the direction. So let's talk about how they work, how they're able to achieve this. So the basic idea is that you've got a motor here that you want to control, and you're going to use MOSFETs or other transistors to do this. Now, transistors act primarily like switches, so I'm going to actually draw them as switches on the board just because it's easier for me to draw, first of all, and also I think it's easier to see the idea of what's going on if I draw it that way. Okay? So when I draw the switches, just translate that into transistors, right? So basically you've got a motor here, and then you've got 4 transistors. So you've got 2 up here, you've got a positive voltage supply, and then you've got 2 more transistors down here. And then you've got ground. Okay? So what happens to the motor when all of the switches are open like that? Is it going to turn? No. There's no path for the current to flow at all. So the motor doesn't turn. But what we can do is we can close 2 of these switches at a time. So if we close this switch up here and this switch down there, we leave the other 2 open. Now the electricity has a path to flow through, right? Now it can flow down from the positive supply here, go through here, goes through the motor this way, and it goes down to ground. And this is going to make the motor turn in one direction. I don't really know which way it's going to turn, but for the sake of argument, I'm just going to say it makes the motor turn that way. Okay? So when the electricity is flowing through like that, it makes the motor turn in that direction. We'll call it clockwise. Okay? So we can make the motor turn in that direction. Now I'm going to open these switches back up. So the motor would stop turning. And now I'm going to close the opposite pair of switches. Okay? So if I close this opposite pair of switches, now the electricity is going to flow through from the positive supply down here through this switch. It's going to go through the motor in the other direction. So now it's going through that way. And it's going to flow down to ground. And since the electricity is flowing through the motor in the opposite direction, it's going to make the motor turn in the opposite direction. Okay? So that's how the H-bridge works. You close one pair of switches to make the motor turn in one direction. You close the opposite pair of switches to make the motor turn in the opposite direction. Okay? Questions about that? Remember, I'm calling these switches, but really they're transistors that are acting like switches. Okay, so that's how we control the direction that the motor is turning, but I still haven't said how we control the speed, right? Well, last time we used PWM to control the speed. So we're going to use that trick again, okay? But this time we're going to put an extra switch down here at the bottom. Again, I'm saying switch, but it's actually another transistor. So we're putting an extra transistor down there, and we control this transistor with PWM. Okay? So we use these switches up on the top to control the direction, and then we use this one, we modulate this with PWM. Basically, we open and close it really fast, and that determines the speed of the motor. So if we have a high duty cycle down here, that means the switch is closed most of the time, the electricity is flowing most of the time, so the motor is moving pretty fast. A low duty cycle means that the switch is open most of the time, less electricity flows, and the motor slows down. So, any questions about that? Yeah?
This switch transistor is same kind of transistor or different?
You can use any type of transistor that you want. We're going to use the same kind that we used last time. Yeah.
It's still a MOSFET transistor though.
Yeah, we're using MOSFETs in this case, but you could do it with BJTs also. If you were using a really big motor, you could do it with a type of switch or a type of transistor called an IGBT. And we'll talk about those in a later lecture. But the principle is the same. Other questions? Okay, so that's a little bit about H-bridges and how they work. So let's talk about a preview of tonight's lab. So the first thing that you're going to do is that you're going to build a circuit pretty much like this. So you're going to control the direction of the motors, but you're not going to control the speed. Okay? So there's a circuit in your lab book that shows you how to do that. And then once you get that built and working, you're going to add the PWM. So you're going to leave most of the circuit the same. You're just going to add an extra transistor down here between this part and ground. And then you're going to control that transistor with the square wave output from your function generator, just like you did last time. You're going to pull that duty cycle knob out again and vary the duty cycle so that you can control this with PWM and control the speed of the motor. So, any questions about that?
What's the name of the motor that we use?
Oh, I don't know. I mean, these are pretty generic, pretty standard little DC motors. I don't think that they have a special name. You can find these in most hobby shops in Fry's and stuff like that. So it's just a little DC motor. Other questions? Okay, cool. Then I will take attendance and I'll let you get started.